Hello everyone, and thank you for attending the conference. My name is Aleksandar, and today I will talk about Apache Kafka and its integration with the Functional Scala codebase. The presentation title is Functional Programming and Kafka. Do they mix? The short answer is yes, they certainly do. However, if you're interested in learning more about the topic, please stay and enjoy the presentation. Here are just my GitHub and Twitter handle, along with the email address and personal blog. And please feel free to reach out to me regarding this talk or anything related to Scala. Now, let's proceed and review the presentation agenda. In the first part of the presentation, I will discuss Apache Kafka. We will explore what it is, its core components, and the significance of Kafka in streaming software architectures. Following that, we will examine the advantage of using Scala and functional streaming approach over the official Java client. And lastly, I will demonstrate the most common patterns with Kafka and Scala. The first question is, what is the Apache Kafka? It's one of the most popular projects in the world of backend development and infrastructure for the last 5 years, but probably even more. And I have a feeling that is definitely here to stay because the real-time data insights are more and more important for a lot of businesses. And Kafka is one of the few battle-tested solutions in that area, maybe the only one. So Kafka is distributed streaming platform, and it's a just definition from the official website documentation. But in a nutshell, you can look at it just as a message broker. It's a distributed, scalable, and reliable solution that enables publish-subscribe messaging model. Kafka is usually run as a cluster, and each node in a cluster is called a broker. Broker is just a server that has a Kafka node running on it, and it's identified by the broker ID. Kafka cluster is used to store unbounded streams of data into something that is called a topic. And you can think of that as a table in a relational database, for example, but without any relational constraints. Every topic is identified by its name, and the number of topics per cluster is basically unlimited. So you can create as many topics as you need. Now, when we are familiar with basic Kafka terms, like what is broker, what is a topic, we can go through some typical Kafka workflow. Here on the left side, we have a Kafka producer, which is used to send data to a particular topic. Topic is usually divided into one or multiple partitions, and they are distributed among different brokers in a cluster if that is possible. Every partition is append-only log, which means when a message is sent to a topic, it will be put at the end of the one of partitions. Partition is also immutable, and once message is there, it can be modified. Kafka achieves resiliency through replication, and the replication factor can be set through configuration when you're creating a topic. It's just a number that specifies how many copies of a topic you want. For example, if you set the replication factor to 5, it will create 5 copies of your topic on different brokers, if that is possible. Every record in Kafka also have the offset, which is incremental ID, and it's one of the most important concepts when writing stream processing applications that works on top of Kafka. Kafka guarantees message ordering, but only at the level of partitions. This just means that the message with a higher offset will be newer. Records in Kafka are kept for a limited amount of time, and that amount is configured by the parameter that is called retention period. And the default retention period in Kafka is 7 days, but you can keep data in your Kafka cluster forever if you want, even though it's not considered as a good practice. There's much better and cheaper ways to store cold data than a Kafka cluster. When the retention period expires, Kafka will trigger the process that will go through all topics, and it will remove all the messages that are older than the retention period, but the offsets in topic and partitions will not reset. They will just keep increasing. Another important concept that is related to Kafka producer is that you can assign a key to your producer record. Every Kafka record is a key value pair with just some additional metadata like offset and time step. Key is optional, and if you do not specify key, messages without it will be distributed among different partitions, usually in a round-robin fashion. But on the other side, all records with the same key will end up in the same partition. So why is this useful? I will give you a simple example. So imagine that we are building an application where we want to collect temperature data for some location. And in that case, we would probably want to keep all temperature data for one location to the same partition to simplify some future aggregations and calculations that we want to perform on our temperature data stream. And only thing that we have to do is just to pick location ID or location name as the key for those messages. Partitioning is done automatically by the producer API, but if you need some custom partitioning strategy, you can implement your own and pass that to a producer and tell them to use a custom partitioning. Now, when we have some data in our Kafka cluster, we would probably want to read it and apply some business logic on our messages. For that task, we will have to use Kafka Consumer API, and consumers are usually grouped into consumer groups, and each consumer in a consumer group will read from a mutually exclusive partitions of a topic. On this slide, we have a topic with 2 partitions and a consumer group with 2 consumers, and you can see that each consumer has its own topic. Also, it's a good practice to run like those 2 producers as separate processes. You should also be aware of a fact that if you have more consumers than you have partitions of a topic, some of the consumers will be inactive, which is just a waste of the resources. On the other hand, if you have more partitions than consumers in a consumer group, some consumer will get multiple topics that are assigned to them, and that's perfectly fine. Consumers are reading records from the topic sequentially, and after the message is consumed and processed, offsets should be committed. This is helpful when our consumer crashes. It will know what was the last committed offset, and it will continue consuming where it left off before the crash. So let's summarize what we have learned about Apache Kafka. Its core API consists of a producer and consumer API, and we talked about them. But it also has Kafka Streams and Kafka Connect APIs, which are a bit more high level, and they're built on top of producer and consumer API, but they are out of scope for this presentation. Finally, some of the most common Kafka use cases are inter-service communication. Kafka is usually used as a data backbone for data-intensive platforms. And finally, the most obvious use case is just building a real-time data pipeline and doing stream processing on top of your Kafka cluster. Now, let's delve into the fun part of the presentation, exploring the reasons for choosing Scala and functional streaming approach. Here you can see what is the typical Kafka consumer program will look like that uses just the official Java client. There's just a loop method that receives Kafka consumer and a processor function that represents our business logic. It's a function from consumer record to unit, and as a functional Scala developers, we don't like that, but at least it's better than any to unit, right? So the loop method will just run indefinitely, and in each iteration, it will just pull batch of records from Kafka. It will apply processor function to every record, and it will commit offsets after processing. Committing offsets just informs the Kafka consumers that messages have been processed and are no longer needed. While there is nothing inherently wrong with this approach, for a Java user, the Scala ecosystem offers the superior solutions. And these alternatives are built on top of official Java client and leverage powerful streaming abstractions from libraries such as FS2 or Zio Streams. The official Kafka client is robust, but quite low level, and implementing relatively basic techniques like parallel message processing can be challenging. Additionally, incorporating some retry logic for failed computation within your data processing pipeline can become messy. Also, complex streaming patterns such as aggregating incoming records up to a given timeout or employing different windowing techniques need to be manually implemented. While it's possible to accomplish all of this with a plain client, it can be quite complex. And as developers, we often don't have time to focus on these problems since building product features is usually a higher priority than just solving the same problem over and over again. Thankfully, we have well-tested solutions like FS2 or Zio Streams that provides a comprehensive API to handle these complex scenarios. So to demonstrate how you can use Kafka in your Scala project, I will utilize Cats Effect and FS2 Kafka library for all the examples, but everything can be pretty easily translated, for example, to Zio and Zio Kafka. First, let's begin with the basics, creating producers and consumers. The recommended approach is to use Kafka producer.resource method, which will just take Kafka producer settings as the input, and it will return FS2 Kafka producer that is wrapped in a Cats Effect resource. We all know what the resource is. It's the widely used data type in functional Scala code bases, and it just ensures, in this case, that producer is properly closed after use. Similar principle applies when creating consumers. So, like producers, consumers can be created using the recommended approach that ensures proper management of resources and their closing after use. Lastly, let's see how we can combine producer and consumer resources to create a final resource that will just return a tuple containing both producer and consumer. So in most applications, single producer and consumers are sufficient. However, in a more complex scenarios, it may be required to use multiple consumers. But keeping stream processing applications small and focused on performing a single task is generally a good practice. Additionally, it's recommended to reuse producer for multiple topics whenever it's possible. In this slide, we will review a more realistic example of consuming message, processing it, and publishing output to another Kafka topic, and finally committing the offsets. So the first step is we are just loading our configuration, we are creating resources, and finally, first we will have to use subscribe to method from FS2 Kafka consumer to subscribe to a configured topic, and after consumer is subscribed to a topic, we can use records method. Then that is just going to return FS2 stream that emits record from the subscribed topic. Each record is a committable consumer record, which is internal FS2 Kafka data type, which contains both the Kafka record and associated offsets that can be used to commit records consumption. The map pacing operator is used to apply enrich record function to each incoming record in a parallel with a concurrency limit of 10. The enrich record function will just transform the original record in some way, and it will return a new key-value pair. And in the map operator, we are just creating producer record, and finally we are just pairing that with the original offset that we are going to use later. The map async is used again to concurrently produce the message to a Kafka topic, and after the record is sent, we are committing offsets of the originally consumed record. Finally, we are using compile and drain methods of the which just essentially tells FS2 to run stream from beginning to end without emitting any values, effectively processing all the messages and committing their offsets as they are processed. This is a typical example of small stream processing application, and so-called the event-driven architectures are just a collection of a lot of small services like this. They just use Kafka or any other messaging solution to receive a message, then you enrich that message or react on the message in some way, and finally publish that to some new topic or a queue, and that will be just consumed by some other downstream service. In order to demonstrate some more complex scenario where we want to run some additional process besides our Kafka processing pipeline, like maybe running HTTP server, let's move the code from the previous slide in these two methods. Creating Kafka processing pipeline is the same, but we added the HTTP server method. Here we are using make HTTP server method, which returns HTTP4S server wrapped into a resource. And to start that server, we just need to pass a function that takes acquired resource and returns the I/O that never completes in this use block. Essentially, this keeps HTTP server running indefinitely until it's interrupted or terminated externally. The IO never function returns an IO that never completes, as I already said, effectively modeling the infinite loop. And this is precisely what we want for our web server, just to run forever. So here we are modifying our application to run both server and Kafka processing pipeline. But if you actually start this application, you will see that only HTTP server will start and the Kafka processing pipeline will not. I guess you already know what the problem is. We both know that HTTP server is long-running process, but also Kafka pipeline is a long-running process. They will run indefinitely until some exception, for example, is raised in one of those processes. So we know what the solution is to run them as a separate processes, or we can run them on separate fibers in this case, since we are using Cats effects runtime. And in order to do that, we just need to invoke start method on those IOs, and it will launch both of them in parallel. So here's the full example. For comprehension, we have two fibers that are running concurrently. One is running HTTP server, and another one is running our Kafka processing pipeline. In order to properly react on a failure of both processes, we need to use raise pair method, which will wait for the termination of the fibers. Basically, it will just return the outcome of the first fiber that is completed, and it will return the other running fiber. And it's usually just used to, for example, cancel that fiber that are still running. But it depends on the use case. Without raise pair, one of our fibers can fail, and another one can keep running. And again, it depends on the use case, but we just want to be aware of that and maybe to shut down the whole application if one of our components in the app is not working. So raise pair gives us a way to react on a fiber termination how we want. after the race page, we are getting the outcome. And in this stage, when we are folding out the outcome, we're just saying that if our server crashed, we just want to cancel our pipeline fiber and close the application, and vice versa. If something is wrong with our Kafka pipeline, we'll just kill the server also and close the application. But besides shutting down the application, we can try to recover from a failure. Maybe we can try to restart our server, or if our pipeline is failed, maybe we can just restart the consumer, recreate it, and start pipeline again from scratch without even shutting down the whole application. We came to the final part of the talk. It will be like really short, but I just wanted to share 2 easy tips that you can use to improve performance of your Kafka consumers. The first tip is how you can parallelize topic processing, and another one will explain why you should avoid frequent offset commits. In the previous consumer examples, I've used the consumer.records method, which will just return a stream of Kafka records that are fetched from all partitions of a subscribed topic. But in order to process all partitions in parallel, we can use partition stream method, which will then return a stream of records for only one partition. So we have here one stream where the elements are streamed that continuously emit records for just a single partitions. Since this is just, as I already mentioned, stream of streams, we can use parjoin unbounded method from the fs2 library to process all inner streams in parallel. And the number of inner streams will be the same as the number of topic partitions. Also, here you can see that I've used Kafka consumer.stream method to create consumer in a stream context instead of a resource. But no matter which approach you prefer, you have to subscribe to a topic first before running the stream. And if you forget to subscribe, there will be not subscribe exception that is raised in the stream. So that is a pretty important part. And another, even easier tip is to avoid frequent offset commits. Most of the consumer applications need at least once message delivery semantics, and in that case, you have to manage offsets manually. In the previous examples, you saw that we can commit offsets by invoking the commit method after a message is processed. But actually, we don't need to commit every offset, only the last processed one. There is a trade-off in how much reprocessing we have to do when we restart versus the performance implications of committing every offset. So depending on the situation, you will have to choose appropriate frequency for offset commits. So in this example, we are using commit batch within method that comes with the fs2 library, and that will just commit every 500 offsets or every 15 seconds, whichever happens first. For at least once delivery, offset commit has to be the last stage if in your stream processing pipeline, and anything that happens after offsets are committed can be part of at least once guarantees. And this is the main reason why batch commit function will just return unit, as they should always be like the final step in your Kafka pipeline. And that's it. Thank you.
Okay, that was a surprise. Do we have questions? Yeah, we do have a question. I see Mikołaj raising his hand. Up there on the right, my right.
Well, now everyone knows my name. So the question is, How is repartitioning/rebalancing handled in this particular code? Because it's not handled explicitly, so it might be handled implicitly somehow, or not.
It's not handled, but yeah, the repartitioning is the most complex part of the Kafka pipelines, but it really depends on the use case, how you want to react. And also, I just forgot to mention, if you are using like a custom assignment of partitions and topic, then you don't have control of rebalance. You will have to handle like everything by yourself.
Okay, anybody else who would like to ask a question?
Hello, what happens when the process record fails or times out or?
When commit fails.
No, when you process the record, but it somehow fails. I don't know, you want to send an email, the email server is down, or the database is down, or something like that. Does Kafka handle it, or do I have to like manually catch that exception?
Yeah, you should definitely handle that manually. Maybe you can incorporate some retry logic, but yeah, it's pretty much Kafka don't have like any mechanism that can help you with failed computation inside your pipeline. But the one important thing, so you should not commit offsets until you are 100% sure that you've done everything that you want.
Yeah, that was my second question. What happens to the offset? Okay, thank you.
Yeah, if you commit the offset and computation failed, it's like it's never happened.